Sigmoid function. Let us learn about sigmoid function, which is used as an activation function in neural networks. What did we learn about activation functions? We learned that activation functions are used in neural networks whenever you want to introduce non-linearity into your model. So the next question is, how is sigmoid function doing this? In this lecture, we are going to go deep into this particular function called sigmoid function. We'll see what it is, how it is introducing nonlinearity, and most importantly, what are the specialities or qualities of this particular function which qualifies it as an activation function. This is the most important part that you want to understand. What specialities do this particular function have that qualifies it as a good activation function? Okay. So the first thing is, what is a sigmoid activation function? A sigmoid function, it is a mathematical function that maps any real number or real value into a value between 0 and 1. This is the speciality of a sigmoid function. What advantage do you get when you map a real value to a value between 0 and 1? One thing that can directly come to your mind is, when it is between 0 and 1, you can interpret it as a probability. This is a very big advantage. We'll see what all are the specialities as the lecture progresses. First of all, let us understand the sigmoid function and then we'll go to the specialities. Okay? As of now, you understood it is some way of mapping any real number to a value between 0 and 1. Okay? Next thing is, what exactly is the formula for this? What is the mathematical formulation? So, sigmoid, generally represented as sigma of x, the equation is 1 by 1 plus e raised to minus x. This is what you call as a sigmoid function. What is e here? E, as you would expect, it is the Euler's number. What is the value of Euler's number? It is something like 2.718 something. This is the Euler's number. And what is x? X is your input value. So given any input value x, when you take sigmoid of x, you get 1 by 1 plus e raised to minus x. Now let us see each of the specialities of this particular formula. First thing you have to understand is what values it is going to take according to different values of x. Let us say your x is having a very large negative value or a small value. A small value is a very large negative value. If this is the case, if your x is taking very large negative value, then think about this. What happens to e raised to minus x? Before that, what happens to e raised to x? If your x is very large, we have to see both the cases. One is it is large positive number and the other one is x is very large negative number. We'll understand both these cases. If x is a very large positive number, then what happens to e power x? After this, we'll understand e power minus x. Why? Because e power minus x is 1 by e power x. So if you know what happens to e power x, then you automatically know what happens to 1 by e power x. Okay. So e power x, we know it takes values from 0 to infinity. So if your x is a very positive and large value, then your e power x, this will take a value which is larger than 1. Then as it becomes larger and larger, that is as x becomes larger and larger, your e power x will also become larger and larger. This is the way it goes. If this is the scenario, that is if e power x exponentially increases when your x increases, then what happens to 1 by e power x? If I am saying e power x is going to take very large values as my value of x increases, then value of 1 by e power x should decrease. This is the logic. Whenever e power x value is taking very large values, 1 by e power x should be taking very small values. So from that, what can you understand? If your x is taking very large positive value, see, I'm taking this positive case first. because that will be easier to understand than the negative value. It's easier for you to understand with a positive case. So when x is taking very large positive value, e power x will also take very large positive value, which means e power minus x will take a very small value, right? If e power x is a very large positive value, then e power minus x, that is 1 by e power x, it will take a very small value. If it takes very small value, then what will be the situation of sigmoid function? Just think of this. If this e power minus x, if this is a very small value which you can almost ignore, then what happens? Then you can ignore this term. Then it becomes 1 by 1, which is 1. So that means whenever your x is largely positive, your sigmoid function of x, this will approach 1. This is what you have to understand from here. The root is clear, right? Whenever x is very large, your e power x will be very large. If e power x is very large, e power minus x should be very small but positive, slightly above 0 or just near to 0. Then you can almost ignore this e power minus x if x is very large. If that is the case, then 1 by 1 plus e power minus x, that will be almost 1, right? This is how your sigmoid function will take at max value 1. Next scenario is, we already explored one end of the spectrum, that is, we know range is from minus infinity to infinity. In that, we already know what if x takes infinity. Next is, what if x takes minus infinity, if it is a very large negative value? In this case, what happens? Your e power minus x, this will be a very large value. If e power minus x is a very large value, then what happens? 1 by 1 plus e power minus x, that will approach 0. So your sigmoid of x, this will be nearly equal to 0. Why is this nearly equal to 0? Because this time your e power minus x value, this will be very large. So very large means it is almost infinity. So then your 1 by 1 plus e power minus x, that will be almost 0. So this is how sigmoid function takes value from 0 to 1. So what did you understand now? Whenever x is very large, almost infinity, then sigmoid function will approach 1, and whenever x is very small, minus infinity, then sigmoid function will approach 0. This is the first thing you have to understand. Next thing, very important thing is, what happens when your x is equal to 0? Whenever your x is equal to 0, then your e power x is equal to 1. E power x, e power minus x, everything is going to be equal to 1 when x is 0. Which means when x is equal to 0, in this case, this will be 1 by 1 plus 1. That is, if e power minus x is 1, this will be 1 by 1 plus 1, which is 1 by 2, that is 0.5. Which means when x is equal to 0, your sigmoid of x will take value 0.5 when x is equal to 0. These are the very basic things. After this, we are going to build on this, okay? Now you understood that it takes values from 0 to 1 when x is very small, that is very large negative number, then it takes 0. When x is very large, that is very large positive number, it takes value 1. In the middle, exactly in the middle, when x is equal to 0, it takes value 0.5. One important question here is, if this is the scenario, why is it called as a sigmoid function? Why do you call this function sigmoid? The reason is, the graph of this looks like a sigmoid. What is sigmoid? Sigmoid is S-shaped. If you draw the graph of the sigmoid function, it will look something like this. That is, if this is my function, this is my graph, this is my x-axis, this is my y-axis, I have my 0 here. How does my sigmoid function graph look? It will look something like this. This will be the graph of a sigmoid function, S-shaped. And this is where you have the value 0.5. So as the value of x increases, your sigmoid function will go towards 1. As the value of x decreases, your sigmoid function value will go towards 0. This is what you have to understand about sigmoid. Next thing is, why is sigmoid used in a neural network? So first thing is that it introduces non-linearity. From the graph itself, you can understand that it is introducing non-linearity. The graph is not a linear graph. It is not a straight line. So it is introducing non-linearity into your model. Second thing is, a very important thing is interpretability. What is interpretability? At the beginning of the lecture, we discussed that when the value is between 0 and 1, you can interpret this as the probability. This is the biggest advantage. In machine learning, many times you want to output probabilities, and that is where sigmoid comes handy, because this value which is between 0 and 1, this you can interpret as probability. When it is 1, that means 100% probability. If it is 0, 0% probability. So whatever value is in between, that you can interpret as the probability. This interpretability is a very important factor, reason for considering sigmoid function as an activation function. The most important factor that you will understand only if you understand about derivatives. So first thing, let us see what is the derivative of sigmoid function. Then we'll come back. At that point, you will actually understand why this is good for a neural network. Okay. So let's first see what is the derivative. A sigmoid function. I'll erase these things off. Okay. So my sigmoid function looks like this. Sigmoid function, sigma of x. This is 1 by 1 plus e power minus x. If I take the derivative of this with respect to x, what happens? This is the most important question. What is the importance of derivative? You know that whenever you want to train a neural network, a model, then you have to first pass input to it, take the output, calculate the loss, and this loss has to be back propagated through the model. And in order to back propagate, or when you are back propagating, how do you decide how much should each parameter be updated? That decision is based on the gradient. So whenever you have an activation function, the gradient of that activation function plays an important role, because that is based upon what you are going to update the parameters. Let us see the derivative of sigmoid. So this will give a lot of insight, because derivative of sigmoid is a very important factor and it adds a lot of specialities. So once we find the derivative, we'll see about those things. Let us take the derivative. With respect to x, I am going to take the derivative. So sigma dash of x, which is the derivative, will be d by dx of 1 by 1 plus e power minus x. So this is just the sigmoid function. Let us see what I can do. So if I want to take the derivative of this, first thing, this can also be written as 1 plus e power minus x whole raised to minus 1. So instead of writing 1 by 1 plus e power minus x, I wrote it as 1 plus e power minus x whole raised to minus 1. This is a cleaner way of writing it when you want to take derivatives. First of all, when you do d by dx of this, what happens? This will become minus 1 into, or I'll simply put a minus here, 1 plus e power minus x whole raised to minus 2. How did this come here? Because d by dx of x power minus 1 will be minus 1 into x power minus 2. That is how this became. Okay. After that, what do I have to do? I have to take derivative of this term. So when I take derivative of this term, what will be d by dx of 1 plus e power minus x? This will be e power minus x derivative is e power minus x, and then you want to take derivative of minus x, d by dx of minus x. This will give you d by dx of minus x will be minus 1. So this is minus 1. Minus 1 into e power minus x is minus e power minus x. That is why I can write here as minus e power minus x. Okay. So now my derivative is in this form. Here I can see there are two negative signs, one here and one here. I'll cancel both because this is a product. It will become 1 plus e power minus x whole raised to minus 2 into e power minus x. Next thing I'm going to do is, e power 1 plus e power minus x whole raised to minus 2 can also be written as, instead of writing it like this, I would like to write as e power minus x divided by 1 plus e power minus x the whole square. Both these are one and the same. Now, instead of writing this whole square, what I can do is, I'm going to separate out the terms so that you clearly understand what I'm doing. I'll do e power minus x divided by 1 plus e power minus x into 1 plus e power minus x. I divided it into two terms. Again, if I have e power minus x here, I can also write it as 1 by e power x, which means I can take this e power x to down. Here I can take it. So then it becomes 1 by e power x into 1 plus e raised to minus x into 1 plus e raised to minus x. From here, do you see the possibility of taking this into a cleaner state, into a clean formula? So that's what we are going to do now. So finally, the derivative of sigmoid is going to look very clean. That is where we are trying to take this to. Next, what can I do? This e power x is here standing alone. So can I take this inside any of these? Yes, I can take it. Then what happens? 1 by, I'm taking this e power x, I'm going to multiply with this. Then it becomes e power x plus, what is e power x into e power minus x? It will be 1. So e power x into e power minus x means e power x into 1 by e power x. This will be 1. So these two will cancel out. This will be e power x plus 1 into other term will stay as it is. 1 plus e power minus x. What can I do from this point? From this point, I somewhere see the formula of a sigmoid here, because I know sigmoid of x, this is 1 by 1 plus e raised to minus x. So somewhere I see that formula here. What I want to do is, I want to single out that part, and for the remaining part I want to see how I can write it properly. So if I want to single out this part, this will be 1 by 1 plus e raised to minus x. I am taking this part aside. Other part will be 1 by e power x plus 1. So I know this part is sigmoid of x and the other part has to be something else. That is what I have to find out. While I want to find out, one thing I'll show you here is, if this is sigmoid x, then what is, okay, I'll just draw a boundary here. Then what will be the value of 1 minus sigmoid of x? If this is my sigmoid of x, then what will be the value of 1 minus sigmoid of x? This can be written as 1 minus 1 by 1 plus e power minus x. This is right. If I can write this way, then I can unify both these by taking this term to the numerator. Then this will become 1 plus e raised to minus x minus 1 divided by 1 plus e raised to minus x. So here this one and this one will cancel out. So this will become e raised to minus x divided by 1 plus e raised to minus x. Next thing I want to do is, e raised to minus x means 1 by e raised to x. So this I am going to again expand here. So here, instead of this e power minus x, I am going to write 1 by e power x. So 1 by e power x whole divided by 1 plus 1 by e power x. This 1 plus 1 by e power x, I can write it as e power x plus 1 by e power x. Okay, this will be e power x plus 1 divided by e power x. Now you can see this e power x and this e power x will cancel out, and what remains? 1 by e power x plus 1. So this exactly is what we have here. So what did you understand at this point? You know, first term, this is same as sigmoid of x, and the second term, this is same as 1 minus sigmoid of x, which means you can write this as sigmoid of x into 1 minus sigmoid of x. So the derivative of sigmoid, sigma dash of x, can be expressed in terms of sigmoid. This is a very big advantage, and I'll tell you what. See, Where are you going to use the derivative? You are going to use this derivative when you want to backpropagate. So when are you going to backpropagate? Let us say you have a model here. This is your model. There are a lot of layers in the model. You gave input here, which is x. You took the output. You found out the loss. Then you are backpropagating the loss. The point here is, during your forward propagation, see, when are you able to backpropagate? Only after you did forward propagation, you reached here, then only you will be backpropagating. During your forward propagation, anyway you are calculating your activation function, which means sigmoid of x is already calculated during your forward propagation journey. So, during your backpropagation, when you want to take derivative of sigmoid of x, you don't have to calculate everything again. Instead, you can simply make use of the sigmoid of x, the activation function that you calculated during your forward propagation. During your forward propagation, you calculated sigmoid of x. Now, during backward propagation, what can you do? You can just take that value and do that value into 1 minus that value. You don't have to separately find out the derivative and calculate. Instead, you can simply make use of whatever you already calculated during your forward propagation. So this is a very big advantage of using sigmoid function. Next thing, derivative you understood is sigmoid of x into 1 minus sigmoid of x. What does this tell you? When I say this derivative is like this, that means you know sigmoid of x is already a value between 0 and 1. So this sigmoid of x is already a value between 0 and 1. Then 1 minus sigmoid of x will also be a value between 0 and 1. If sigmoid of x is between 0 and 1, then 1 minus that value will also be between 0 and 1. If that is the scenario, then what can be the maximum value of this derivative and what can be the minimum value? Just think about this. That is, if this is the scenario, the problem is if you multiply two numbers which are lesser than 1, that is something like 0.7 into 0.7, what is going to happen is during multiplication it is going to take an even smaller value. That is, if you multiply these two, you will get 0.49, which is an even smaller value. But here, because one side is sigmoid of x, other side is 1 minus sigmoid of x, you can't have 0.7 on both. If this is 0.7, automatically other one will be 0.3, which is 1 minus 0.7. So, what is the maximum value possible? If you simply think, you will directly understand this. If sigmoid of x is equal to 0.5, this is the case where maximum value is possible for the derivative. And that value, that is sigma dash of 0, will be 0.25. So the maximum value the derivative of sigmoid can take is 0.25. What did you understand from this? This means your sigmoid of x can take all these values, but when that is from 0 to 1, any of the values can be taken by sigmoid of x, but the largest value is occurring when sigmoid of x is in the middle at 0.5. But the problem here is, if you go to the either extremes, that is, if you take a very large value, if your value of x is very large on the positive side or negative side, if it is large on the positive side, sigmoid of x value will be close to 1. If it is large on the negative side, sigmoid of x value will be close to 0. In either cases, the problem is derivative is going to be, that is sigma dash of x is going to be very close to 0. When derivative is close to 0, what is the problem? Slope will be 0. It will always be a straight line. That is why your sigmoid function has this shape. That is, when you go to the either extremes, whenever your x is larger on the negative side or on the positive side, your slope is 0. At this point, slope becomes almost 0. Same here as well. Slope is almost 0. But when your sigmoid takes something in the middle, something near to 0, that is when your slope is maximum. That is where you get largest derivative. Okay. So what does this mean from a neural network point of view? This tells you that whenever your value is positive, then neuron input, that is whenever your neuron input is very positive, then sigmoid curve almost flattens out. So on both sides, whether it is very positive or very negative, both sides your sigmoid curve almost flattens out. So one more thing, how will the graph of this sigmoid function look like? I told you graph of sigmoid is this, graph of derivative. If I draw graph of the derivative of sigmoid, you know at 0.25 it takes larger value. But there is a big advantage of this derivative, that is on both sides it is symmetric. If you see the sigmoid function, it is not symmetric. On both sides it is different. But coming to the derivative, it takes large value at 0.25, the peak value, and it is a bell curve on both sides. Bell curve on both sides. On both sides, when x is larger, slope is almost 0. That is what you see here. On both sides, slope is almost 0. Here also slope is 0. Here also slope is 0. In the middle, slope is very large. That is what you see here. This is the graph of sigma dash of x, derivative. This is the graph of sigma of x, the sigmoid function. Okay. So the point you have to I understand here is the steepness that you have is identical on both sides, be it on the positive side or on the negative side. So the learning strength of your model, that would depend on how much is the input on either side. That is, it does not depend on the direction. Learning is same on the both sides, because of which it is a good activation function. That is, on either side you have same magnitude of learning. Irrespective of the direction, you will have similar learning on both sides, plus your learning will be maximum here. Okay, so this is what you have to understand about sigmoid function. What are the most important points? First most important point is, first thing is it introduces non-linearity. Second thing is it introduces interpretability. You can interpret as probabilities. Third thing, most important thing is the advantage that you are getting is, because the derivative is simply sigmoid of x into 1 minus sigmoid of x, calculation is easier. That is, during forward propagation, you already have sigmoid of x. So during backward propagation, you can use that value and find out the derivative. So this is a big advantage of sigmoid function. Plus you have to keep in mind whatever are the characteristics, that is the maximum slope is when x equal to 0. Then as you go towards either sides, the slope diminishes, derivative diminishes. That is what you can see here. That part, whether it's a positive or negative quality, that we'll discuss in the coming lectures. For now, just understand that slope decreases as you go to the either sides. Whenever it takes larger value, be it positive or negative, slope decreases in case of sigmoid function.